So, good evening, everyone. Let us continue our discussion and start the course contents of for the 8th week of this rehabilitation and retrofitting course. So, this week we will be basically concentrating on pavement rehabilitation. So, how to rehabilitate pavement using concrete overlay. So, the first lecture will be basically on concepts of concrete overlay. So in this lecture, we will basically be covering introduction to concrete overlay, characteristics of pavements, and types of concrete overlay. So a layer of design thickness over an existing pavement is called the concrete overlay. It is a strategy for pavement rehabilitation to improve its performance in terms of its strength and riding quality and service life, a measure of structural strengthening of existing pavement, both bituminous pavement and concrete pavement. It needs proper design considering vehicular load, existing pavement condition, and climatic conditions. So there are basically two types of concrete overlays. One is existing concrete pavement and one is existing asphalt pavement. So inside existing concrete pavement, it is of three types: bonded concrete overlay, partial bonded concrete overlay, and unbonded concrete overlay. Whereas in the case of existing asphalt pavement, it is of three types: conventional white topping, thin white topping, and ultra thin white topping. So the selection of overlay, it depends on the type of existing pavement, condition of existing pavement, traffic condition on the pavement, geometric constraints such as curb and gutter sections, guardrails, shoulder widths, vertical clearances, etc., and desired service life. The benefits of overlay are increase in structural and functional capacity of existing pavement, less maintenance, not susceptible to moisture or temperature, smooth riding, less fuel consumption, reduction of urban heat island UHI effect due to light color, more reflective to light and less heat absorption, and enhanced durability and low life cycle cost. So, the characteristics of pavement are: pavement is a structure that carries vehicular load which is constructed over a prepared foundation or subgrade. They are basically of two broad types: bituminous pavement and concrete pavement. The pavements are provided on highways and expressways, major and minor district roads, urban roads like arterial roads, collector roads, local streets, airports, runways, taxiways, aprons, intersections, and uh, your parking areas, haul roads and loading yards, service roads, toll plaza, bus terminals, shoulder, and low volume roads. So this is an example of a bituminous road which is black in color. Okay, so this is the ideal road which people want for driving, and this is the concrete road. Okay, so it is whitish silvery color. Okay, as we all know the color of concrete. The main components of a bituminous pavement are bituminous surfacing. So this is asphalt or bituminous mix, a mixture of bitumen and aggregates. Then there is base layer, which consists of wet mix macadam WMM, waterbound macadam WBM, cemented base consisting of soil or aggregates stabilized with cement, fly ash, lime fly ash or other materials, subbase layer, unbound layers like natural sand, muram, gravel, laterite, conker, etc., or bound layers consisting of soil aggregate or soil aggregate mixture modified with cement, lime, fly ash, etc., and subgrade. So apart from that, there is a layered structure, that is layers which are arranged in the order of descending strength and load carrying capacity. So each load layer contributes in carrying and distributing loads. Each layer receives load, spreads and passes only to the next layer, and the load transfer by grain to grain contact occurs. So that is the characteristic of bituminous pavement. The structure behaves like a flexible sheet due to traffic loading, and performance is based on overall performance of all layers. So this is basically the schematic diagram of bituminous pavement, as you can see. So this is the surface. Okay, so below the surface there is base, then subbase, and at last there is subgrade. Okay, So performance is based on the overall performance of all the layers because they are not very strong. So this is the that was basically the bituminous pavement. Now here it is the concrete pavement. Okay, so in concrete pavement the main components are the concrete slab, base, which is dry lean concrete cement treated layer, subbase, that is water bound macadam and wet mix macadam, and then there is subgrade. Okay, and transverse joints, longitudinal joints. Okay, so transverse joints, so they are basically in the form of dowel bars, and longitudinal joints in the form of tie bars. Okay, so this is basically the schematic representation of all the components. So if you compare the concrete pavement with bituminous, that is flexible pavement, you will see that base, subbase and subgrade, all the three are same. Only the surface is here, it is made of bitumen, whereas here it is concrete slab. And apart from that, there is transverse and longitudinal joints. Okay, so transverse joints, that is along the intersection, along the cross section, sorry. So that is made up of dowel bars, and longitudinal joints, which are basically made up of using tie bars. Okay, with tie bars. So they have high rigidity and high elastic modulus of concrete slab. Concrete slab responsible for carrying the load. So that is unlike the case of flexible pavement where the surface was made of bitumen. So every layer actually carried the load. So here basically concrete slab, in case of concrete pavement, the concrete slab is responsible for carrying the load, distributes load on a wider area by bending action, and less influence of subgrade strength. Okay, and so that this strength does not matter that much. And finite slabs with joints. Okay, so there are finite number of slabs with joints. So this is the schematic diagram of concrete pavement. As I told you, base, subbase and subgrade are the same. Only the top layer is made of concrete slab, where in flexible pavement it was bitumen. And also in the concrete pavement they have your this longitudinal joints and transverse joints. So transverse joints are in the form of dowel bars, and longitudinal joints are are made using the tie bars. So in concrete pavement, so there are three types of concrete overlay that can be used for rehabilitation. So those are bonded concrete overlay, partially bonded concrete overlay, and unbonded concrete overlay basically. So let us go through all of them in detail now. So bonded concrete overlay. So here overlay is fully bonded to the existing concrete pavement. So they are basically the overlay and the existing pavement, they are basically bonded together. Okay, so there is a bonding interface. The thickness generally ranges from 75 to 100 millimeters. So this has a thickness of about 75 to 100 mm or 7.5 to 10 centimeter. It is used to improve the structural capacity of existing pavement, surface quality in terms of riding quality, skid resistance, noise, and to correct damages caused by chemical spills, etc. Applicable when the existing pavement is relatively in good condition with no material related distresses but in need of structural enhancement. So that is basically, this bonded concrete overlay is done when the repairing is not that much important, only it needs some sort of structural enhancement. So therefore it is just bonded to the existing pavement, the overlay, and that is why it is called bonded concrete overlay. It is important to achieve proper bonding between a new overlay and old concrete. Requires surface preparation for bonding like cleaning, shot blasting, milling, hydroblasting, etc. to produce a clean and roughened surface. Bonding agent like cement, sand, slurry may be applied. Pre-overlay repair needed to fill up cracks, joints, punch outs, and to remove grease, oils, sealants, bitumen, etc. Matching joints of overlay and existing pavement is necessary. So these are the surface preparation for performing the bonded concrete overlay. So this is the original concrete pavement, and this is the bonded concrete overlay, and in between them the interface is the bonded interface. So that was all about the bonded concrete overlay. Now let us see the next one, which is the partially bonded concrete overlay. So they are placed directly on existing concrete pavement with little surface preparation if required. They are used when the degree of bonding is not critical to the performance of overlay. The thickness ranges from 150 to 200 mm, that is 15 to 20 centimeter. They are applicable when the existing pavement is in fair to moderate condition. Pre-overlay repair needed to fill up cracks, joints, punch outs, etc. Matching joints of overlay and existing pavement surface necessary. Problem of reflection cracking occurs in the partially bonded concrete overlay. So that is one of the problem. Okay. So that is the partially bonded concrete overlay. Okay. So here what happens, because there the degree of bonding is although not critical, but because the condition of the existing pavement is fair to moderate condition, so any existing pavement's deflection, okay, so that is also reflected in the overlay. Okay, so that is called the reflection cracking, because it is, although not fully bonded, it is partially bonded. Okay, so because there is little surface preparation, so therefore and also the condition is not that good of the road pavement, so there is any deflection is seen directly in the overlay. Okay, any rutting or any type of deflection behavior, so that's why the problem of reflection cracking occurs. Now let us go to the third case, which is the unbonded concrete overlay. So that it basically contains a separation layer in between new overlay and existing pavement. So this is the separation layer. So that's why there is no bonding, and hence it is unbonded. Okay. The separation layer ensures independent behavior between the two slabs, thereby minimizing the potential for reflection cracking. Okay. So this type of unbonded concrete overlay is used for pavement which is having a health of fair to poor condition. Okay, so it is very bad. Okay, so if it is directly bonded, then there will be a problem of reflection cracking. Hence, if there is a separation layer of bituminous separation layer of about 100 mm thickness, so this is about 10 centimeter thick, and that is also made up of bitumen, so hence there is no reflection cracking. The thickness of overlay ranging from 150 to 300 mm, so the overlay thickness is about 15 to 30 centimeter, and it is used when the existing pavement is in fair to poor condition with little or no structural life remaining. Okay, so that is the condition when to use unbonded concrete overlay. Then so if we see the typical applications for unbonded concrete overlay, so that is basically to restore or enhance the pavement's structural capacity, to improve surface quality with improved surface friction and noise reduction. Little or no pre-overlay repair is needed because it is having a separation basically, and matching of joints of overlay and those of existing pavement is also not necessary, and it is to be designed as new pavement because there is complete separation, so we can design it as a new pavement. Okay, so it has 10 centimeter of your bitumen layer as a separation layer, so or HMA. Okay, a hot mix admixture or geotextile hot mix asphalt, sorry, hot mix asphalt or geotextile separation layer is present in between, and this is unbonded concrete overlay, and this is existing concrete pavement. So that is the sketch of unbonded concrete overlay. So these are the various types of concrete overlays and concrete pavement. Okay, so bonded, unbonded, and partially bonded. Now let us go to the bituminous pavement and its various types of concrete overlays. So there are basically three. Okay, one is conventional white topping, one is thin white topping, and one is ultra thin white topping. So these are the three types of white topping in bituminous pavement. So this is an example of white topping over bituminous pavement. So let us see all of them in detail. So what is conventional white topping? So concrete overlay on top of existing bituminous pavement. Generally no debonding layer. PCC, that is plain cement concrete layer, laid directly on bituminous surface. So as can be seen here. And so there is no debonding layer. Okay. Directly your PCC layer is directly placed on bituminous layer. Little or no pre-overlay treatment or milling done. Applicable for heavy damaged bituminous pavements with excessive rutting, cracking, shoving, etc. And it is used for improved structural and functional capacity, enhance service life, and reduce maintenance requirements. So this is the conventional white topping schematic representation. So this is the PCC overlay, plain cement concrete overlay above a existing hot mix asphalt pavement, and this is the interface. Okay, so there is no debonding layer as such, we can directly place it above. The concrete overlay of thickness generally 200 millimeter or more, designed and constructed without consideration of any bond between concrete overlay and the underlying bituminous layer, Existing bituminous surface behaves as a base layer to white topping, designed and constructed like a new concrete pavement without assuming any composite action. Joints in transverse and longitudinal directions, similar joint spacing as in concrete pavement, and the transverse joints with dowel bars and longitudinal joints with tie bars. So that was similar to that of concrete pavement. That was about conventional white topping. Now let us go to the thin white topping. So it is a composite action between concrete overlay and existing bituminous layer. Extensive surface preparation is done to promote significant bonding between concrete overlay and the existing bituminous pavement. Bond between overlay and underlying bituminous layer is often a consideration but not mandatory. Bonding may be ignored in design. So bond is optional. We want it or we don't want it. It is not mandatory. Shorter joint spacing, square or rectangular panels, length by breadth should not be greater than 1/1.2, and the thickness ranges from 100 to 200 millimeter. And high strength concrete generally with fibers such as steel, synthetic fibers like polypropylene are used. So this is the example of thin white topping. It is applicable when the condition of the existing bituminous surface is fair, without white cracks, and without material or subgrade related distresses. Okay, so no white cracks and no material or subgrade related distresses. Minimum 75 to 100 mm thickness bituminous surfacing is needed after milling. Okay, so about 75 to 100 mm thickness minimum bituminous surfacing needs to be done after milling. Okay, so these are the requirements. Now let us go to the third one, which is the ultra thin white topping. Okay, so it must be bonded with existing bituminous surfacing to achieve composite action. So because it is ultra thin, so it must be bonded with existing bituminous surfacing to achieve composite action. Surface treatment by milling of the existing bituminous layer to provide adequate bonding of the concrete overlay. Applicable for low volume deteriorated asphalt pavements like local streets, intersections, parking lots that exhibit distresses like cracking, potholes, etc. Applicable when the condition of the existing bituminous surface is fair to good but requires structural capacity enhancement. And high strength concrete generally with fibers such as steel, synthetic fibers like polypropylene. Okay, so these are the characteristics and conditions for ultra thin white topping. So minimum 75 to 100 mm thick bituminous surfacing after milling is required. Much shorter joint spacing of 0.6 to 1.25 meter, square or rectangular panels. Length by breadth should not be greater than 1/1.2, and thickness of overlay less than generally 100 mm. Okay, so surface preparation is 75 to 100 mm bituminous. Okay, and the thickness of overlay is less than 100 mm, so that's why it is ultra thin. So this is the one. So this existing HFMA pavement, this is the mill surface, and we have put here the ultra thin white topping. So that is basically a thin layer of concrete. Okay, and basically your this has to be this requires basically bonding, and it should have a minimum 75 to 100 mm bituminous surfacing after milling. Okay, and these are the length by breadth ratio should not be greater than 1.2. So it should not be basically it should not uh, it should be basically two-way. Okay, if you remember two-way slabs, it should be basically like two-way slabs. So one dimension should not be very much higher than the other dimension. Okay, and the thickness of overlay should be less than 100 mm. So in summary, we can say in this lecture, we basically learned about the various concepts of concrete overlay. We studied the characteristics of bituminous and concrete pavement, and we understood the types of concrete overlay present. So the next lecture, it will be on distresses in existing pavement. So what are the various types of distresses that can be found in an existing pavement? So let us see. So in this lecture, we will cover distresses in both bituminous and concrete pavements and their identifications, how to identify them. So the major reasons for pavement distresses, if we think about, so they can be because of this. Okay, so one is repeated loading due to moving vehicles. So this is the primary reason. Okay, so that results into rutting. Okay, we will see in the coming slides. Then there is overloading of vehicles. Then there is temperature and moisture effects, subgrade failure, deep foundation movement. Then there is material degradation. And apart from that, there is also joint failure. Okay, so these are some of the issues. Okay, so there's the reasons for which the pavement distress can basically occur. And then, and there is that is basically the distresses in pavement. Okay, if we talk about distresses particularly in bituminous pavements, we will find the following. Okay, one is fatigue cracking or alligator cracking. So it is alligator because the cracking seems like the backside of a crocodile. Okay, so like the back skin of the crocodile, the cracks look similar, so that is why it is called alligator cracking or fatigue cracking. Then there is rutting, which is due to the vehicular movement. Then there is corrugations, so formation of wavy shaped surface. Then there is longitudinal and transverse cracking, reflection cracking, we talked about this earlier. Then there is bleeding of surface and potholes, that is a very common problem in India. And also there is polished aggregate. Okay, so some aggregates shine. Okay, so that is also one of the distresses. So firstly, let us see the fatigue cracking or alligator cracking. So that is the alligator cracking. As I told you, the surface, the cracking seems similar to the back skin of a crocodile. Okay, so that's why it is alligator cracking. So that is basically, if we talk about fatigue cracking, it is series of interconnected cracks, excessive repetition of heavy vehicles, particularly in the wheel paths, overloading of heavy commercial vehicles, weakening of subgrade or lower layers of the pavement due to increase of excessive moisture, brittleness of binder due to aging and lowering of surface temperature, and stripping of underlying bituminous courses. So these are some of the reasons due to which alligator cracking occurs. Then there is reflection cracking or block cracking. So this is sympathetic cracks that appear in the bituminous resurfacing at the location of joints and cracks in underlying pavement, differential movement and or movement of the underlying concrete slab as a result of thermal and moisture changes. Okay, so the reflection cracking basically, so they appear in the bituminous resurfacing at the location of joints and cracks in underlying pavement. So this is the existing pavement and this is resurfacing. Basically we are talking about the overlay. Okay, so if the sympathetic or symmetrical cracks appear in the top surface, so that is the reflection cracking. Okay, and differential movement and or movement of the underlying concrete slab as a result of thermal and moisture. So if there is a further, there is some differential movement also, that also results in the same. Okay, and because the shape is like block, we also tell it as block cracking, reflection cracking or block cracking, as can be seen here. Then there is rutting. Okay, rutting is longitudinal depression, that is along the length of the road. Okay, so depression along the length of the road on the pavement surface along the wheel path. Okay, heavy channelized traffic and overloading results in this, and weak pavement due to poor subgrade, and inadequate compaction of the mix at the surface or in the underlying bituminous courses, improper mix design lacking in stability to support the traffic. Okay, so these are the some of the reasons due to which the rutting process basically occurs, as you can see here, rutting. Then there is the problem of corrugation. So corrugation is formation of irregular undulations across the surface. Okay, so it is similar to rutting, but this pattern is little different. Okay, and it is basically formation of regular uh, undulations across the surface. Okay, so it can be longitudinal, it can be transverse anyway. And lack of stability in the mix, such as excessive binder. So basically corrugation does not follow the wheel path. Okay, in the rutting it follows the wheel path. Okay, so that is the main difference. So there is lack of stability in the mix, excessive binder, high proportion of fines, too round or too smooth textured aggregate, too soft binder, etc. Faulty laying of surface cores, insufficient rolling or rolling a tender mix, braking action of vehicles on grade, especially near intersections. So this can be some of the reasons for corrugation to occur. So you can see some depressions. Okay, so this can be seen from this rod basically. Then there is longitudinal cracking. So the cracks occurring along the length of the road, that is the longitudinal cracking. So cracks along the length of the road alternate wetting and drying beneath the shoulder surface. So that is one of the reason. And or weak uh, by improper or weak join between adjoining layers of pavement. Okay, So that can be one of the more regions for this. Okay, and apart from that, there is this transverse cracking. Okay, so that is till now the cracks basically were along the length. Okay, so this transverse cracking, it is along the uh, along the cross section. Okay, so cross sectional cracking, that is the transverse cracking. And the cracks in the transverse directions or as interconnected cracks forming series of large blocks perpendicular to the direction of the road, reflection of cracks or joints in an underlying pavement layer, low temperature brittleness or oxidation of bitumen, and also structural failure at concrete base course, shrinkage of bituminous mix on account of low temperature. So that can be also one of the reason. And so shrinkage is basically reduction of volume. Okay, so of bituminous mix on account of low temp. So as we know, during low temperature objects always shrink. Okay, so reduction in volume occurs. So this is the example of the transverse cracking basically. And then there is this polished aggregate issue, distress. So aggregates exposed on the surface of pavement due to loss of bituminous materials, so they basically shine, and they provide low skid resistance. Okay, and and become slippery when it is wet due to abrasion. Okay, so because they become slippery, okay, due to abrasion, that is repeated uh, uh, basically due to repeated movement of the vehicles. Okay, so the surface get corroded and they wear away. Okay, wearing, so this abrasion occurs and it becomes slippery, and especially when it is wet due to abrasion, and so it results in low skid resistance. Okay, so the skidding, that is basically when an object slides through the surface, so that is not that resistance is very low. Okay, so it has a problem of this may result in the brake failure. Okay, so brake failure in vehicle, so that is one of the issue of polished aggregate. Apart from that, there is potholes. So this is basically localized disintegration of material, okay, on the surface, as can be seen in this representative figure, and loss of adhesion and bituminous wearing coat due to ingress of water into the pavement or due to higher voids in surface, lack of proper bond between the bituminous surfacing and the underlying water-bound macadam base layer, and basically in sufficient bitumen content in localized areas of the surfacing layer. Okay, so main reason is the disintegration and insufficient bitumen content in the localized areas of the surfacing layer, due to which it is not able to bind together the pavement. Okay, so that's why basically lack of proper bonding occurs, and that's why the potholes basically come up. And apart from that, there is bleeding. So bleeding, as we all know, it is when the surface, the basically water or any liquid comes up to the, so fluid comes up to the surface. Okay, so surface having a thin film of excess bituminous binder creates a shiny reflecting surface, and becomes soft in hot weather and slippery in cold weather, and wet weather causes low skid or sliding resistance. So that is in case of pavement, bleeding is due to the bitumen. Okay, so that becomes this also becomes liquid. Okay, in hot weather. Okay, soft and slippery it also becomes in cold. Okay, and also in wet weather. And excessive bitumen in hot mix due to faulty mix design or lapses in quality control, use of softer grade bitumen for the climatic condition, and lower voids in hot mix. Okay, so that this may be some of the issues. Okay, so if these issues are there, and then the chances of bleeding are very high. So these are about the bituminous pavements distresses. Now let us see the distresses in concrete pavements. So here the distresses are fatigue cracking corners, and those basically occurs in corners and edges of slab panel. Then there is transverse and longitudinal cracking, spalling at joint, faulting at joint, blow up at joint, punch out and pop out. Okay. So let us see one by one each. So one first is corner cracking. So high stress development due to repeated and or overloaded vehicles, excessive drying shrinkage stresses, excessive thermal and moisture gradient stresses, unstable subgrade or loss of subbase support, poor load transfer at transverse joints due to dowel bar restraints, and this is results in the corner cracking. Okay, so then there is longitudinal cracking. So this large joint spacing, inadequate depth of joint, late joint saw cutting, loss of subgrade support, poorly compacted subgrade, settlement of embankment which leads to subsequent settlement of slabs, sudden change in thermal or moisture gradient, different subbase or subgrade types having different modulus of elasticity and thermal properties, and drying shrinkage. So these are some of the reasons of longitudinal cracking. Then there is again transverse cracking, that is cracking along the cross section. So that is development of high tensile stresses due to overloading, excessive dry shrinkage stresses, inadequate depth and or late initial joint cutting, excessive joint spacing in transverse direction, excessive subbase restraint, settlement or poor subbase support at localized area, incorrect location of transverse joints at or over cross drainage structure or utility duct. So these are the reasons for transverse cracking. Then there is spalling from bed construction joint. So as we remember, if you remember, so spalling was basically the removal of the surface. Okay, removal of uh, cracks. Removal of layers from the top surface. Okay, so when it is high, it is called as spalling basically. So if the thickness is high, it is spalling. If the thickness of the removal of top layer is low, it is delamination, if you remember. So this spalling, it occurs from bad construction joint, damage of concrete at or near the joints due to excessive stresses caused by ingress of stones, that is the movement of stones, uh, dust, okay, and other incompressible materials into the joint, thus damage the functioning of joints. Repeated traffic loads at slab ends, mechanical damage, defects in dowel load transfer system, that is the transverse joints basically, where the dowel bars are present. Okay, and then weak poorly compacted concrete, particularly at or near joints. Okay, so that can also be a reason. So this is the spalling at joints, okay, which is occurring. So as you can see here, then there is the faulting at joint. Okay, so this is the basically the faulting. Okay, so if you see, there is a vertical movement. This the lower slab is there, lower slab has a vertical declination. Okay, so it is a vertical settlement occurred, vertical movement occurred of the lower slab as compared to the higher slab. It can be measured in this, it can be seen from this small rod like shape structure. Okay, so or scale. Okay, so if we see what is faulting a joint, so this is a relative vertical movement of adjacent slab panels, causes poor riding quality and reduction in load transfer along transverse joints or cracks, ingress of water, causes internal erosion and pumping along longitudinal joints, settlement of subgrade or shoulder drop off caused by heavy traffic, differential settlement support due to inadequate foundation. So these are some of the reasons for faulting a joint. Then there is blow up a joint. Okay, so if you can see, uh, both have blown up. Okay, and so there is a rise in this joint. Okay, rise in elevation in this joint. Okay, so blow up edge joint is basically accumulation of incompressible material in the joints, reduces joint width, okay, and excessive expansion resulting from combined adverse thermal and moisture conditions. Okay, so these are the reasons for which blow up joints occur. One is incompressible material, and second is excessive expansion from combined thermal and moisture conditions. Then there is pop out. Pop-out is loss of contaminated or non-durable concrete pockets at surface, and lack of homogeneity, uniformity, and consistency of the mix. Okay, so these have come out. Okay, and loss of aggregate from concrete surface, thermal expansion, freeze thaw, etc., and inadequate compaction. So these are some of the reasons for popping out. Then there is punch out. Okay, so if you can see here, this is a punch out type of distress. So this is basically part of slab broken out due to formation of several closely spaced cracks near joints. Okay, So if you can see here, near the joints there are various closely spaced cracks. Okay, closely spaced cracks, and due to which part of slab has been broken. Okay, so in CRCP it can be caused by steel corrosion. Okay, and inadequate amount of steel reinforcement. So this can be the reason for this punch out and loss of sub base support. So that can be also one of the reasons. So basically it is a broken part of a slab, okay, due to formation of several closely spaced cracks near the joints basically. So in this lecture, we basically tried to understand the various types of distresses, both in bituminous and concrete pavements, and also we went through the reasons for these distresses and also tried to identify the distresses. The next lecture will be on the evaluation of pavement. So in this lecture, we will basically be covering the evaluation of a pavement. So how to evaluate the condition or the health of a pavement. So evaluation of pavement performance. So the pavements deteriorate over time due to age, heavy and repeated traffic loading, climatic variations, poor subgrade condition, pavement material degradation, and poor drainage. The rate of deterioration different for different types of pavement. It is necessary to evaluate functional and structural performance periodically. The need for maintenance and rehabilitation of existing pavement can be assessed based on the results of performance evaluation. Okay, so these are the various criteria we have to see. Okay, so the functional performance, so it is related to comfortable, safe and economical riding from the road users. So this functional performance, so that is basically related to the comfort, safety and economy, okay, in riding for the road users. And they are evaluated based on three parameters. One is the surface condition, which is cracking, rutting or potholes presence. Second is roughness. Okay, so what is the type of longitudinal profile? Okay, so better the roughness, better the performance. And one is the skid resistance or sliding resistance. What is the resistance to sliding? Okay, sliding your sliding pattern. Okay, so what is the resistance for that pattern? So that is the skid resistance. So to determine the so basically functional evaluation of pavement is done to determine the surface condition or functional performance of existing pavement at a given time. The visual distress survey by walk and drive to identify the location of distresses, and to determine the type, extent, severity with measurements and recording of data. So the visual distresses are surveyed by walk and drive, by walking by foot and driving by vehicle. The amount of cracking, rutting, pothole, friction, skid resistance, etc. in meter per kilometer or meter square per kilometer length of pavement and or percentage of total length is done, okay, evaluated. And the pavement roughness or longitudinal profile by direct measurement of pavement responses in meter per kilometer. So this is the way of functional evaluation for pavement. So as you can see here, so there is visual and by foot, and for visual so for visual distress survey by walk and your walk and drive. Okay, so this is walk and this is drive. So this using the straight edge, we can see the deviation, the deflections, okay, longitudinal depressions. And here if you can see the bump integrator, so it has and there is the profilometer. So there are some advanced techniques, okay, so that is going through understanding those are beyond our course. So basically these are some of the ways how by drive also you can find out the functional evaluation. Then there is the FWD, which is the falling weight deflectometer. So we will be coming in those, okay, in the coming slides. So that is all about the functional performance. And the second is the structural performance. So that is related to the structural adequacy of the pavement. There is the in situ or at site strength of different layers of pavement, load carrying capacity of the pavement. So for that, basically, we go for semi-destructive testing. So first is the extraction of cores and testing of the core samples in laboratory to estimate strength, moisture content, density, layer thickness, etc. Okay, so using typical core samples, coring of pavement using core cutter. Okay, so that is done basically. And then there is crush composition and trial pit on an existing bituminous pavement. Okay, so there uh, basically people go for trial pits. Okay, so pit is trial pit is excavated. Okay, and this basically it is done at suitable intervals on both sides of carriageway. Okay, so in order to evaluate the structural performance or evaluation of structural evaluation of pavement. So it is basically used to determine the crust composition and to estimate the strength of subgrade and the soil characteristics, and like grain size, distribution, dry density, moisture content, Atterberg limits, etc. by testing of soil samples in laboratory. So these are basically geotechnical studies. Okay, so these are done using the trial pit. Okay, so small mining is done, and using this they can both sides of the road two-way, and they find out the performance. Then there is non-destructive, that is semi-destructive, and then there is non-destructive testing, that is NDT. So that is application of static or dynamic load on the pavement and measuring the corresponding pavement responses, generally deflection, to estimate the in situ strengths of different pavement layers by back calculation. So using deflection, you back calculate and find the estimate the in situ strength. Okay, so there's NDT, which is very much preferable, ideal. Okay, and that can be done using three ways. One is the plate load test. Okay, so that is very common. Then there is Benkelman beam deflection test, and then there is falling weight deflectometer test. Okay, so that is FWT test. So let us go through that. Falling weight deflectometer, so it is an NDT equipment. Okay, and that can be in vehicle or inside the vehicle or trailer mounted. Okay, so it can be carried outside the vehicle or it can be inside the vehicle too. Okay. So it is versatile equipment for evaluation of several parameters. The strength estimation of different pavement layers is done. The estimation of remaining life can be done. Determination of strengthening or overlay requirement, if any, can be found, and the estimation of joint performance is also done. Okay, so in IIT Kharagpur, okay, so they have developed different models of falling weight deflectometer. So this is the trailer mounted, and this is the in vehicle FWD model. So in vehicle FWD model, basically the falling weight deflectometer is present inside the vehicle itself, whereas in the trailer mounted FWD model, so this FWD is present here, and it can be connected to a truck. Okay, truck or lorry, so that is a trailer, so that is mounted. Okay, so you have to connect it from outside externally. So this is internal FWD, this is external FWD. So the working principle, okay, if we talk about that, so it is an impulse loading device simulating the load of a moving vehicle. So the impulse load is applied on the pavement by means of a falling mass. The mass is allowed to drop vertically from a predetermined height on a system of springs placed over a circular loading plate. Different magnitudes of impulse load can be obtained by selection of a suitable mass and an appropriate height of fall. And the measurement of applied load by load cell. Okay, so the applied load is measured by a load cell. Under the application of impulse load, pavement surface deflects in the form of a bowl, which is also called as deflection bowl. The pavement surface deflections are measured using a number of displacement sensors like geophones. Displacement sensors are fixed on a frame at different radial distances, which is placed on the pavement surface for measuring deflections. Load and deflection data are recorded and stored by a data acquisition system. Okay, DAS. So this is the working principle of FWD. If you can see, this is the falling mass, this is the spring, this is the loading plate, and these are the deflections. Okay, deflection bowl, if you can see, because the shape is like a bowl. Okay, and these are the sensors, deflection sensors. So by measuring the deflection, you can back calculate and estimate the in situ strength. Okay, so that is the concept of falling weight deflectometer. So if we can see here the major components, so it consists of a circular loading plate which is 300 mm to 450 mm in diameter with a 5 mm thick rubber pad glued at its bottom. Then there is falling mass, which is 50 kg to 350 kg between range. And for heavier models, the falling mass can be from 200 to 700 kg. The falling height is between 100 mm to 6300 mm, that is from 10 centimeter to 630 centimeter. And basically your this so basically if we talk about, so our room, basically one floor is around 3 meter. Okay, 3 meter is 3000 mm. So this is 6300 mm, that is above two floors. Okay, so about around two floors, the height is around two floors, so that is maximum. So the target peak load, it is between 40 kilonewton to 60 kilonewton. So it is corresponding to one dual wheel of standard 80 kilonewton axle load, and the loading time is 15 to 50 milliseconds, corresponding to a moving vehicle to cross the length of a tire imprint at a speed of 60 km per hour, which is in the range of 20 to 30 meters. Okay, so that is basically the condition or the criteria. Then the load cell, it should have a minimum resolution of 0.1 kilonewton. The number of geophones that has to be installed is 6 to 9 with minimum resolution of 1 micrometer. Geophones positioned on a rigid frame at radial distances 0, 300, 600, 900, 1200, 1500 and 1800 millimeter from the load center. And the calibration of load cell and each geophone before testing needs to be done. Okay, so this is the loading plate, and these are the geophones attached on a frame. Okay, to basically measure the deflection bowl. Okay, and if you can see here, so this is a typical FWD load pulse. Okay, so it is a plot between load and time in milliseconds. Okay, and this is a typical geophone responses. So this is the velocity of geophone and the time. Okay, so the test procedure is such: identify firstly the test point on the pavement, then center the load plate over the test point, lower the load plate on the pavement to ensure proper contact, lower the frame holding the geophones so that the transducers are in proper contact with the pavement surface, and raise the mass to a predetermined height required for producing a target load of 40 kilonewton. So that is the main condition. Okay, so the target load should be 40 kilonewton, and for that we have to raise the mass to a predetermined height. Okay, so drop one sitting load, then raise the mass and drop, record load and deflection data into the computer through a data acquisition system. If the applied load peak load differs from 40 kilonewton, the measured deflections need to be normalized to correspond to the standard target load of 40 kilonewton, because 40 kilonewton is the standard target load. So minimum 3 readings at each point needs to be taken, and record air temperature and pavement temperature too. So then that is the experiment. Okay, so after that we need to back calculate. So back calculation of pavement layer moduli. So from the measured load and deflection data and using the inputs like layer thicknesses, Poisson's ratio values of different layers, loading plate radius, radial distances of geophones, the elastic moduli of different layers of the existing pavement are back calculated using an appropriate technique. Iterative approach in which the moduli values of each layer are varied in each step, and the computed and measured deflections are compared. Iterations continue till a satisfactory matching between the measured and computed deflections is attained. Okay, so it is a closed form solution. Okay, and closed form because we get an we basically we get to an merging solution. Okay, so because it is an iterative process, we get the actual value. Okay, and therefore your it is not an approximate solution. Okay, so that is a closed form solution, we get an actual value. And optimization techniques and machine learning techniques like ANN, artificial neural networks, genetic algorithms, etc. are used. And the softwares for bituminous pavements are various types like ELMOD, EverCalc, BizDef, Mitchback, Modulus, Padel, KGPback, etc. And there are softwares for concrete pavements too, such as ILLI BACK, PEDD, NUS BACK, BAKFAA, DIPLO DEF, CAL BACK, etc. Okay, so These are the various softwares used in the FWD test for bituminous and concrete pavements respectively. This figure basically shows the typical locations for FWD testing, if you can see in a road. Okay, so this, the star represents the geophone positions, and this octagon basically it represents the load positions, as you can see here. So these are the this is the load position, and these are the geophone positions. Okay, and this is a transverse joint, that is the having dowel bars, and these are the longitudinal joints having tie bars. Okay, in a pavement, and this is the paved soldier. So this is the main road. Okay, so this is the FWD testing near joint. Okay, so this is the joint, and the FWD testing is done here. So this is the interior loading condition. Okay, and this is the load position at number 4 in here. Okay, this is the result. And so that is all about the test. So in this lecture, we studied the functional and structural evaluation of pavement, and the structural evaluation could be done by your Benkelman beam test, and then there's plate load test, and also the famous one is FWD, that is falling weight deflectometer. So we studied about that, how to use that for structural evaluation of pavement. Okay. So the next lecture will be the design considerations for concrete overlay. In this lecture, we'll be covering the design considerations for concrete overlay and the distresses in the overlay. So, the information that needs to be collected from existing pavement evaluation are type and thickness of existing layer, width of existing pavement, type and extent of distress, restriction on finished road level, that is FRL, presence of treacherous soil like black cotton soil, surface and subsurface drainage condition and drainage requirements, and traffic survey data. So if you remember the concrete overlay, so that can be different for both existing concrete pavement and existing asphalt pavement. For existing concrete pavement, we had used three types of concrete overlays, which are bonded, partially bonded, and unbonded concrete overlays. On the other hand, for existing asphalt pavement, we use concrete overlays in the form of white topping, which could be conventional, thin, and ultra thin. Okay, so in conventional, no bonding was required. In thin, it was up to us. Okay, but in ultra thin, the bonding was mandatory because of very less thickness. So, if we talk about the concrete overlay over bituminous pavement or white topping, okay, so there were three types: conventional white topping, thin white topping, and ultra thin white topping. So, conventional white topping, so it is unbonded to existing pavement, if we just discussed, and is applicable for heavily damaged bituminous pavements. Okay, so for heavily damaged bituminous pavements, conventional white topping is used. The thin white topping, it is bonded, partially bonded, or unbonded to existing pavement. So it is up to our wish. Okay, we want it to bond, unbond, or partially bond, and it is used for applicable for pavements of moderately fair condition without white cracks and without material or subgrade related distresses. Okay, so the condition is better than the heavily damaged bituminous pavements, that is where conventional white topping is used, that is without moderately fair condition, without white cracks, and without material or subgrade related distresses. And then there is thirdly there is ultra thin white topping, so that is bonded to existing pavement, so bonding is must, and it is applicable for pavements having condition fair to good but requires structural capacity enhancement. Okay, so the condition is pretty fair or even good, but it requires structural capacity enhancement, then ultra thin white topping is used. So the design considerations for white topping are as such. So the concrete overlay, it provides necessary strength to deteriorated pavement. Entire existing bituminous pavement with its different layers and the subgrade below it, it is considered as the foundation as a whole for the concrete overlay. Existing bituminous pavement should have moderate to fairly good strength to act as base layer. Minimum thickness of existing bituminous layer should be 75 to 100 millimeter after milling. Okay, and so subgrade with sufficient strength having no major distress or subgrade failure. Okay, so then it is used. Okay, so the subgrade strength, which is expressed in terms of modulus of subgrade reaction K or CBR. Okay, so 2 uh, I forgot the full form of CBR. If I am correct, it is California Bearing Ratio. Okay, so that is used in transportation engineering. So it is the subgrade strength. It is expressed in terms of the modulus of subgrade reaction K or CBR. It is to be determined by carrying out plate load test and or investigation of the soil samples from trial pits and coring. The strength of existing bituminous layer is to be determined by carrying out BBD test or FWD test. So this is Benkelman beam deflection, and FWD is falling weight deflectometer. Okay, so the strength of existing bituminous layer, it is to be determined by BBD FW. So the subgrade strength is to be determined by plate load test, and the bituminous existing layer strength to be determined by Benkelman beam deflection or falling weight deflectometer test, basically. And the effective modulus of subgrade reaction on top of bituminous layer to be estimated from correlation charts using BBD test data or from correlation charts developed using plate load test data. So it is up to our wish. So this is the correlation chart, okay, for effective K value on top of existing bituminous pavement from Benkelman beam deflection values. So this is the characteristic Benkelman beam deflection in millimeter, and this is a K value on top existing AC pavement, which is kg in kg per centimeter cube. Okay, so these are some of the further correlation chart. So this is the K value. This is a K is basically the modulus of subgrade reaction. So effective K value over existing bituminous pavement at top of granular subbase, and this is effective K value over existing bituminous pavement at top of cement treated base. Okay, so various bases. So there the correlation charts are shown, and if you see here, the composite action of concrete overlay an existing bituminous layer for thin and ultra thin white topping. So that is required. Okay, so for thin and ultra thin white topping, composite action of concrete overlay and existing bituminous layer is required. Surface preparation to promote significant bonding between concrete overlay and the existing bituminous pavement. A surface of existing bituminous layer to be rough to achieve bonding and uniform, to provide identical thickness throughout the overlay. And the design is influenced by traffic characteristics, interface characteristics, and climatic conditions. So all the three play a part in the design: traffic, interface, and climatic conditions. So how, let us see. So one first is the traffic characteristics. So traffic service to be carried out for a minimum of 3 to 7 days, 24 hours, to estimate uh, the base year traffic and the future traffic on the pavement. So minimum 3 to 7 days for each 24 hours to estimate the base year traffic and the future traffic on the pavement. It needs to be done. The survey of traffic needs to be done, and the composition and magnitude of axle loads is necessary. Positions of axle loads on the pavement is necessary. Tire pressure, frequency of each type of axle loads, total number of commercial vehicles per day, that is CVPD. Okay, so this is a term very commonly used in traffic engineering. And then there is traffic growth rate. Okay, so these are all used in traffic characteristics. Then there is interface characteristics. So for fully bonded overlay, the existing bituminous layer provides additional stiffness to the concrete overlay. The stress developed in overlays less, thickness requirement is less. Okay, so that is in fully bonded overlay, that is mainly in white, your ultra thin white topping. Okay, so the existing bituminous layer provides additional stiffness to the concrete overlay. The stress developed in overlay is less, that is thickness requirement is less. For unbonded condition, the underlying bituminous layer has no contribution in providing additional stiffness. There's no sharing in tensile stresses. Stress developed at the bottom of overlay is more than that for the bonded case. Okay, and hence thickness requirement is more. So basically, in unbonded condition, that is in conventional white topping, the stress developed at the bottom of overlay is more than that for the bonded case, because here no contribution. Okay, because the bonding is not there, so the underlying bituminous layer does not provide any additional stiffness. Okay, so the stress is very high in the bottom of overlay, and therefore thickness requirement is more. Okay, So that is, as you can see here, the stress diagram for bonded and unbonded interface conditions of overlay with existing asphalt layer. Okay, if you see here, so this is the unbonded interface. Okay, so in the unbonded interface, the stress is much higher. Okay, and in the case of bonded interface, it is less. Okay, because it has been carried into the asphalt. Okay, so that is the interface conditions characteristics. Then there is climatic conditions, which is basically the effect of temperature. So there is curling effect due to daily variation in temperature. So as you can see here, so slab curling during daytime and slab curling during nighttime. So this can be self-explanatory. So in the daytime, the temperature at top, okay, is higher than the temperature at bottom. So when the temperature is higher, it will elongate. Okay, so that is because of coefficient of thermal expansion. So delta L will be higher at top. So that's why the curling will be basically it will be basically concave downward. Okay, so it will be concave downward, and in the night time, because the lower temperature at top will be less, so at down the extension will be more elongation. So that's why the concavity is upward. Okay, so that is slab curling during night time. So how climatic conditions affect, that is climatic conditions have an effect based on temperature. So there is curling effect due to daily variation in temperature. Temperature differential within the slab depends upon the thickness of slab and the geographic location of the road stretch. Slab may curl up or down when the temperature at the top is higher or lower than that of the bottom, basically. And curling is restrained by adjacent slabs and slab self-weight. Curling stresses are developed at top or bottom of slab. Curling stresses also depends on panel size. Curling effect prominent for negative temperature gradient. Temperature at top surface is lower than that of bottom surface. So that is at night basically. During night time, while it is not so significant for positive temperature gradient, that is temperature at top surface is higher than that of the top surface. Sorry, this is bottom surface, I'm sorry for that. So that is the curling effect basically. And this basically is the schematic diagram of thin or ultra thin topping, white topping. So this is dual wheel load, and this is typical saw cuts up to 1/3 slab. Okay, depth to form joints in transverse and longitudinal directions, and this is a transverse direction. Okay, so these are some of the design considerations for thin to white thin, ultra white thin to ultra thin white topping. Okay, and then effective strength of foundation to be considered. Foundation comprised of existing bituminous layer and subgrade. Critical stress due to axial loading and temperature gradient. Location of critical flexural stress, corner, top and edge bottom of panel. Negative temperature gradient more influence on critical stress. Critical stress depends upon slab size and bonding condition. Less panel size, less flexural stress develops. Less bonding, more flexural stress develops. So these are some of the conditions, and load transfer through aggregate interlocking action is done, achievable. So then there is critical stress criterion. The flexural stresses develop due to the effects of wheel load, temperature gradient and their combinations at the top or bottom of slab, edge or corner should be less than the flexural strength of the pavement quality concrete, that is PQC. And then there is fatigue criterion. The pavement should be able to carry the total repetitions of all the axial loads moving on the pavement throughout its design life without fatigue failure. Then the stresses which are present in concrete overlay. So it can be corner cracking, transverse cracking, longitudinal cracking, spalling, then joint faulting and edge uh, breaking. Okay, so these are the distresses. So these are the photos of the distresses taken from the various sources. So in this lecture, we basically studied the design considerations for concrete overlay and white topping, and also we went through the distresses in the concrete overlay itself. So the next lecture will be basically studying the construction of concrete overlay. It will basically cover the overlay materials, the construction of white topping. So the overlay materials can be of following types. It can be PCC or plain cement concrete. It can be FRC or fiber reinforced concrete. It can be HPC, that is high performance concrete with mineral lead mixtures. Then it can be high performance fiber reinforced concrete, okay, HPFRC. Then it can be high strength concrete and SCC, self compacting concrete. And the characteristic compressive strength of concrete is taken as 40 megapascal or more, so at least 40 megapascal after 28 days. So the ingredients basically, as we all know, it is cement, sand, coarse aggregate, okay, and water, okay. And so these are the main constituents of concrete. And then there is water reducing admixture, that is chemical admixture, maximum 2% by weight of cement. And then there is mineral admixture, which is SCM, supplementary cementitious material. So it can be silica fume, blast furnace slag, fly ash. So silica fume maximum of 3 to 10%, blast furnace slag maximum 70%, and fly ash maximum 25%. And also air entraining agents are basically required for mainly the freezing thawing issues. And also uh, so that there is adequate space for your curling effects and other effects to negotiate, okay, so it can balance out, no distresses occur. So it should not be greater than 6.5%, okay, ideally it should be between 10%, 1 to 10%. So here in roads it should not be greater than 6.5%. So apart from that, fibers can be there. It can be the concentration can be 0.2 to 0.4% by weight of cement, and it can be in the form of micropolymeric fibers such as polypropylene, polyethylene, etc. Then there is macropolymeric fibers and macro steel fibers, and fibers general properties and requirements. So the diameter should be 10 to 70 microns, and it should have a specific gravity of 0.91 to 1.34. Water absorption should be less than 0.3%. Melting point should be greater than 160 degrees centigrade. And no formation of fiber balls should be seen, and no adverse effect on concrete, obviously. So these are some of the examples of overlay materials. This is micro polypropylene fibers. These are macro polymeric fibers. And these are macro steel fibers. So the construction of overlay, so it can be pre-overlay treatment and paving of overlay, okay. So these are the types. The pre-overlaying overlay. So basically, the two steps are there. One is before overlay, the treatment, that is pre-overlay treatment, and second stage is the paving of overlay. So during the pre-overlay treatment, we basically perform three tasks. One is the milling, okay, or cutting off the top surface. And then there is repair of existing pavement, okay, if some repairment is required. And thirdly is the cleansing, okay, the cleaning of the surface. So that is a pre-overlay treatment. So milling basically it is the surface preparation measure to remove the top bituminous layer damage due to cracking, patching, rutting, or by other distresses, to make the surface rough and uniform to ensure adequate bonding between the existing bituminous layer and the new concrete overlay. Equipment used is the milling machine, and the depth of milling is between 25 to 75 millimeter depending on the extent of damage. The hand grinding or light chiseling may also be done locally. And after milling, a minimum thickness of 75 to 100 asphalt layer must be retained basically. So that is about the pre-overlay treatment. So the damaged bituminous pavement, as you can see here, and this is the chiseling of damaged surface, and this is the milling of surface using milling machine, okay. So these are very high-tech instruments nowadays which are present for the pre-overlay treatments, okay. So then uh, there is uh, so there is the repairment, so that is firstly the removal, okay, removal of the surface, the surface layer which has been affected, okay, so that is milling. Then there is the repairment of the existing pavement, so that is the second stage, second step inside the pre-overlay treatment. So after milling, surface needs to be repaired to fill up the local patches, if any local distresses like cracks, potholes, etc., to be filled up, sealed with dense bituminous mixes to minimize reflection cracks. And top of the mill surface and the repaired surface after patch repairing should be at the same level. A profile correction layer of bituminous macadam of minimum thickness of 50 mm may be provided on the mill surface. So that is the second stage, and the third is the cleaning stage. Okay, so here in cleaning, basically what we do is removal of any loose materials, dust and debris to ensure adequate bonding between the existing bituminous layer and the concrete overlay, and that is done using manual brooming, power brooming, air blasting, water blasting, sand blasting, etc. So these are the techniques, okay, brooming and blasting, through which the cleaning can be done. And so basically, if we see in the case of conventional white topping, it does not require much pre-overlay treatment, okay, because no bonding is required. However, in thin and ultra thin white topping requires adequate surface treatment because there is a condition of bonding, okay. And here there is the general pavement condition and the required treatments, okay. So if the rutting is less than 2 inches, okay, so then we either we require little bit of milling or no milling, okay. If the rutting is more than 2 inches, then we need milling or leveling. If shoving is there, then milling. If potholes, then fill with crushed stone, coal mixture or hot mixture. If there is subgrade failure, then remove and replace or repair. If there is alligator cracking, block cracking, transverse cracking, longitudinal cracking, revealing bleeding, we don't need any type of treatment. Okay. Then the equipment, basically, so this is slip from paver, okay, and this is fixed form paver. So this both of them are, I think you have seen this commonly in the road construction, okay. So these two types of paver are used for the pavement of paving of overlay, okay. So this is slip form and this is fixed form, and that basically uses concreting, okay. So concreting is basically the placement of concrete mix, the compaction with vibrators, surface finish, bull floating and texturing or tining, curing with curing compound, and also by wet gunny bags for 28 days, formation of construction joint with dowel bars, okay. So that is basically in the transverse joint after a day's work. And then there is a saw cutting of transverse and longitudinal joints within basically 18 to 24 hours of concreting, that is within 1 day, okay. So this is basically the concreting using fixed form paver, as you can see here. And this is the bull floating, this is texturing, and this is saw cutting of joints, basically. So joints have been cut here, and so this is a finished surface of white topping, okay. So white topping, finished surface, as you can see here. And so we can say in this lecture we basically studied about the materials required for the concrete overlay and the construction of white topping, okay, which is done above the bituminous pavement, okay. So with this we come to the end of the lecture section for the 8th week. Now let us go to the solve problems and understand the notes better with some solve problems, okay, questions. So first question, bleeding is observed in A, flexible pavement, B, rigid pavement. So if you remember, bleeding, it is basically distress in bituminous pavement. It is a surface having a thin film of excessive bituminous binder with which creates a shiny reflecting surface and becomes soft in hot weather and slippery in cold and wet weather and causes low skid resistance, sliding resistance. So that is the basically the bleeding, okay. It becomes liquid, so it occurs in the bituminous, that is flexible pavement. So a flexible pavement is the right option. Second question, statement 1. In case of unbonded concrete overlay, matching of joints of overlay and those of existing pavement is necessary. Statement 2. Unbonded concrete overlay contains a separation layer in between new overlay and existing pavement. A. Only statement 1 is correct. B. Only statement 2 is correct. C. Both the statements are correct. Or D. None of the statements is correct. So which is the correct option? So unbonded concrete overlay contains a separation layer in between new overlay and existing pavement. So this is correct, okay. Unbonded means it contains a separation layer, okay. And in case of unbonded concrete overlay, matching of joints of overlay and those of existing pavement, so it is not necessary, okay. So this is wrong, okay. So in case of unbonded concrete overlay, matching of joints of overlay and those of existing pavement is not necessary. So statement 1 is wrong, only 2 is correct. So B, only statement 2 is correct, is the right option. So that has been told here also. So separation layer is present and it does not require. Okay, so it is independent. Okay, so B, only statement 2 is correct, is the right option. Third question, in which overlay the potential for reflection cracking is least? A, bonded concrete overlay, B, partially bonded concrete overlay, C, unbonded concrete overlay, D, all of the above. So if you remember what is reflection cracking, so if in the existing pavement, if there is some type of deformation, and that is also basically it is transferred to the overlay. Okay, so that is basically reflection cracking. So that will be transferred only when there is some type of bonding. Okay, so that is possible in bonded concrete and partially bonded concrete. Okay, but in the case of unbonded, because there is no bonding, okay, so there is complete separation with a bituminous layer, so there is no reflection cracking occurring. So C, unbonded concrete overlay is the right option. So as you can see here also, minimizing potential for reflection cracking, unbonded concrete overlay. So C, unbonded concrete overlay is the right option. Fourth question, this is generally not used when the existing pavement is relatively in good or moderate condition with no material related distresses. A, bonded concrete overlay, B, partially bonded concrete overlay, C, unbonded concrete overlay, or D, all of the above. So which is not used when existing pavement is relatively in good or moderate condition? So if you remember, unbonded concrete overlay, it is only used when the condition of road is very bad. Okay, so that's why there is a separation, because we can't trust the strength of the existing pavement. So this is only used in bad condition, not in good or moderate condition with no material related distresses. So which is not used? Unbonded concrete overlay is not used in good or moderate condition. As you can see here, it is used when the existing pavement is in fair to poor condition with little or no structural life remaining. That is unbonded concrete overlay. So C, unbonded concrete overlay is the right option. Fifth question, identify the type of failure in concrete pavement. A, rutting, B, faulting, C, bleeding, D, none of the above. So if you remember rutting, it was basically longitudinal depressions along the wheel of the vehicle. Okay, so that is not what is shown here. So A, rutting is not correct. If you remember bleeding, so bleeding is basically it occurs in flexible pavement when the content of your bitumen is much higher and it becomes hot. In hot it becomes soft, and in cold it becomes slippery. Okay, so that is the bleeding process in pavement. So this is basically faulting. Okay, so if you remember, if you see this line, basically this scale, so the above slab is little bit higher, or we can say the lower slab has basically deformed. There is a deflection vertical, and so that is basically called along the basically crack. Okay, longitudinal or transverse crack. So there is a deflection of the lower slab, a vertical deflection of the lower slab as compared to the higher slab. So that is basically faulting. Okay, so relative vertical movement of adjacent slab panels causes poor riding quality and reduction transfer. So relative vertical movement. So that is faulting. So B, faulting is the right option. Sixth question, in which case bonding between overlay and underlying bituminous layer must be considered. Okay, so where bonding between overlay and underlying bituminous layer must be considered, it is mandatory. Is it A, thin white topping, B, conventional white topping, C, ultra thin white topping, or D, all of the above? So if you remember, in conventional white topping the bonding is not required. In thin white topping it is up to our choice, we want to give it or not. But in ultra thin white topping it is mandatory, that is it is must. Okay, so here the question is where the bonding between overlay and underlying bituminous layer must be considered, that is where it is mandatory. So mandatory it is in ultra thin white topping. So C, ultra thin white topping is the right option. Okay, so here it must be bonded, okay, with existing bituminous surfacing to achieve composite action. So the ultra thin white topping is the right option. Seventh question. Transverse cracking is a type of distress observed in concrete pavement which happens due to A, excessive drying shrinkage stresses, B. Excessive sub-base restraint. C. Development of high tensile stresses due to overloading, or D. All of the above. So why transverse cracking occurs basically in concrete pavement? So if you see, it occurs excessive due to excessive drying shrinkage stresses. Okay, so A is correct. So it also occurs due to excessive sub-base restraint. Okay, so B is also correct. And then there is also your development of high tensile stresses due to overloading. So that is also one of the reasons for transverse cracking. So all the options are correct. Okay, so D, all of the above. It happens due to all of the above. Okay, so D, all of the above is the right option. Eighth question: visual distress survey of a pavement by walk and drive is conducted for A. Functional evaluation of pavement, B. Structural evaluation of pavement, C. Both A and B, or D. None of the above. So if you remember, your this visual distress survey of pavement by walk and drive, it is mainly considered for the your conducted for functional evaluation. For structural evaluation, there is NDT and semi-destructive. So if you remember, there is trial pit in semi-destructive, and for non-destructive we went for FWD, falling with deflectometer, and there was Benkelman beam deflection and also plate load. Okay, so those are structural. So there we basically find the deflection and then correlated it with through back calculation we correlated it with the in situ strength. Okay, so that was structural. But functional, we basically, it is visual distress survey of pavement by walk and drive. Walk is by foot, drive is by vehicle. So a functional evaluation of pavement is the right option, as you can see here, walk and drive. Okay, so a functional evaluation of pavement is the right option. Ninth question: identify the test conducted to find out the moisture content of bituminous pavement. A, is it FWD, that is falling weight deflectometer test? B, is it core test? C, pull-off test? Or D, all of the above? So which test is conducted to find out the moisture content of bituminous pavement? So if you remember, we basically use the core cutter. Okay, so that is the core test. Okay, so for finding it is a semi-destructive test for structural evaluation of pavement. So for finding moisture content, we basically use cores, okay, core samples and core testing. So basically core cutter, coring of pavement using core cutter. So core test is done. So B, core test is the right option. 10th question: identify the NDT or non-destructive test conducted for functional evaluation of pavement. A, surface roughness test, B, FWT test, C, plate load test, D, all of the above. So if you remember, if this FWD, that is falling weight deflectometer test, basically it is used for the structural evaluation, that is deflection and in situ strength. Okay, so that is not correct. Similarly, plate load test also basically it is used for the structural evaluation. Okay, that is in situ strength. So C is also not correct. So surface roughness test is the non-destructive test conducted for functional evaluation. Okay, so if you can see here, functional performance. Okay, so it is related to comfortability, safety and economy, riding for the road users. And the surface condition, it is monitored in terms of cracking, rutting, potholes, etc. And roughness is basically longitudinal profile. Okay, and basically so there all those basically we studied about your protrusions and all, right? So those the wavy shapes. Okay, so that is the roughness. Okay, and then there is also the skid resistance. Okay, so that is basically the sliding resistance. So surface condition and roughness, it is basically the functional performance. So surface roughness. Okay, and that is so basically this roughness is also corrugation and all. Okay, so this these are some of the functional parameters. Okay, so surface roughness is the therefore the right option. Okay, NDT test conducted for functional evaluation of pavement can be surface roughness test. So A, surface roughness test is the right option. With this, we come to the end of today's discussion. So let us meet next week's class with the 9th week course content and problem solving, as well as solve problem exercise. Okay, so with this, I would like to thank everyone. Have a good day, good night. Let us meet next class. Bye.